everyone, welcome back. This is the last part of the radioactivity and nuclear chemistry chapter. This is Dr. Rhonda Kofeld of Calhoun Community College. In this part, we're going to look at fission versus fusion, and then we're going to work some problems with mass defect, and then use mass defect to calculate nuclear binding energy. So radiometric dating is used because of this half-life. We know that after so many half-lives, you should have this percent of, or this many grams of a particular component. And so if we take a sample, like if we find an artifact or something, we can take a sample of the minerals and rocks around it and date them and see what these various amounts are. And so, for example, we can use the uranium to lead, U-238 versus lead 206 in your volcanic rocks. Okay, that allows us to make an estimate of the age of the Earth to be 4 to 4.5 billion years old. So when you hear these geological times, that's what they're basing them on. Okay, we're using the half-lives to see how much parent versus daughter nuclide is present in particular areas. And so in fission means split. Okay, fission is split one big thing into two smaller things, whereas fusion is where you take two small things and fuse them together, and then they form a large nucleus. So that's the basic difference between the two. Now obviously it's a pretty complex process because we're smashing nuclei together in order to get them to merge, or we're hitting like uranium with a neutron or whatever to make it bust open, okay, and break that nucleus apart so that it becomes two different things. Both of them release a tremendous amount of energy. They're very, very, very energetic. That's why we've tried to harness this for our energy usage and clean fuel. So in a fission reaction, okay, that is where we are bombarding the nucleus with something, a chain reaction occurs. So when you hit the nucleus with like a neutron, then it's going to bust apart and it's going to produce more neutrons, okay? And so as those neutrons are produced, they're going to find other fissionable uranium, and they're going to bust it open, and then you're going to produce more neutrons. And so you keep going and going and going. So it doesn't take a huge amount of neutrons to start the chain, because once you get it started, it's self-perpetuating. And the minimum amount of fissional isotope you need to sustain that chain reaction is called its critical mass. So when you reach critical mass, that reaction is going to sustain itself. And that's the beauty of it, because once you apply that initial energy, then it's just going to produce energy, energy, energy. Fissionable isotopes are U-235, plutonium-239, and plutonium-240. Those are the ones we typically use. Now, uranium-235 is found naturally in ores, but only about 1% is U-235. Most of it is U-238, which is not fissionable. Okay, so there is not enough U-235 in raw ore to reach critical mass or sustain a chain reaction. So in order to get a fissionable amount, we do what's called enriching the U-235. Now, we only need to enrich it to about 3% for reactor grade. Okay, so we only, it's not a horribly difficult process to enrich that uranium up to from 1% to 3% in the ore. All right, and so that's great. And so we can produce all this energy. Weapons grade, however, has to be enriched up to 90%. So that's why when you hear on TV that they are watching like satellite images of someone that they think they're trying to enrich to weapons grade, it takes a lot more energy and a lot more sophisticated techniques in order to do the weapons grade, obviously. And so this is our critical mass, our chain reaction. So we start out with at least 3% of U-235, okay? And I hit it with a neutron. And that neutron is going to cause it to split open, and it's going to form a molecule of krypton, or an atom of krypton, and an atom of barium-140, okay? But the important thing is, in addition to that, it's going to eject 3 neutrons. Those 3 neutrons are then going to find another, each one of them will find another U-235 atom, split that into krypton and barium, and produce 3 more. So now you started with 1, you made 3, now you've got 9. And it just keeps going geometrically, logarithmically, I guess, until you get to that point where, it's just self-sustaining. And it'll keep on going if you don't control it. So you'll just keep on and on and on and on, and it'll get hotter and hotter and hotter if you don't control the reaction. So this is what nuclear reactors are based on. They use fission to generate electricity. About 20% of the United States is generated through fissionable nuclear power. Reactors mostly use the U-235, at least we said 3% or. Okay, and what happens is, as this reaction is generating this huge amount of energy, it boils water, turns it to steam, and then the steam turns a turbine, which we can then turn that movement into electricity. So nuclear power plants, you use about 50 kilograms of this fuel to generate enough electricity for 1 million people. And there is absolutely no air pollution involved in this process whatsoever. The problem with coal burning plants is it takes 2 million kilograms that we've dug out of the earth, okay, which is not sustainable, to generate that same amount of electricity. It also produces NOx and SOx, which when you get that into the air with rain, produces acid with moisture, and that it will rain down and kill trees and cause discoloration to buildings and also inhalation issues. Okay, you also produce carbon dioxide as part of this process, and that contributes to global warming. So part of the packet that you're doing for the lab is you are looking at these nuclear power plants and how they do things and what it takes and where they're located and all that, to see what you think about, what the pros and cons of what we should do, because the downside of nuclear power plants is waste disposal. Because remember, this is radioactive material when you get done with it, and when you get done with it, you can't make it not hazardous, and so it's going to stay radioactive for years and years and years, because it's U-235, right? So that's thousands of years. And so we just store it. So we can't really dispose of it. We can only store it. Some people say, well, shoot it to the moon. Okay, the problem with that is we know rockets do blow up, and we don't want to barrage the earth with nuclear waste. So anyway, so we actually put them in big storage cases that are lined with clay, and they're going to sit there. Okay, so this is a schematic of a nuclear power plant reactor. And this is in your packet too. So this is the picture that comes from. So you'll be labeling that. But your reactor is here, okay? And you have your reactor is got a big sleeve around it. So this is a cutaway. You have your fuel, okay? Your uranium-235 fuel, and they do it into rods that they can stick down through holes, okay? And then they have something called a control rod. So remember me telling you, if you didn't do something to stop the reaction, that it would just keep going and getting hotter and hotter and hotter and hotter. Okay, so that's called a meltdown. And if you get a chance to watch the Chernobyl documentary that was put out last year, I think, or maybe a few years ago, it's a great depiction of what happens when you don't have enough controls in place. Okay, so what happens is you've got your uranium here, and you're pushing off these neutrons, right? And then neutrons, neutrons, neutrons. And it'll keep on going unless you move a control rod down to block the neutrons. If you do that, then you are slowing down, or you can even stop that reaction from occurring. So what you're trying to do is you want to make enough heat, release enough energy to run your turbines, but control it so that you don't get a meltdown. And in ours, in the United States, we have triple redundancy, even more than that, okay? So that we have, because what happened in Chernobyl is that this cooling water, their cooling water stopped pumping. So they weren't able to cool this down, and it just kept getting hotter and hotter. And so it eventually melted literally through the cement and into the ground. And then it blew up. And then when it blows up, it puts it all into the air. Not good. And then it was going into the water and the soil, and that was not good either. Okay? But cool, because if you've got this, okay, you're pumping, so the water coming from this is radioactive, but it doesn't touch anything. It just goes through this and is recirculated, right? And is pumped back in there. The heat from it, as it goes through the steam tank, it only just like gets the heat from that, but there's no contact with it to that water. And so this is boiled, and the steam goes up, and the steam turns the turbine, okay? And then the turbine generates electricity. And then that water goes down, it condenses because it was steam, so it turns back into water by going through a condenser coil, kind of like you have in your air conditioner. And then you can pump that water back up, or you can waste that water into the river. That's why they always build them on a river, because you have to have a good water source that you're not going to run out of. So you're not going to run out of the river water, okay? And so this is also in a loop, okay? So your radioactive stuff is in this orange colored, okay? And then the non-radioactive is in the blue, which is where your water is flowing to turn the turbine and all that, and that can be released into the river. It's a little warmer when you release it than when you bring it in, but that has to be monitored, because if it's too hot, it'll cause algae blooms and fish kills and things like that. So they got to be really careful about that. But that's true with coal-powered plants as well. All right. So your condenser, which is run by water from the river. So this is basically how they work. You've got to have this cooling water, and you've got to be able to recirculate all of this, okay, so that you can continue to keep that under control. But your control rods are really the things that control the reaction, because if the control rod is between the two uranium rods, then they cannot continue to generate the neutrons, and so that can slow it down. That's how you keep it under control. And if you ever, you could Google it or whatever, but the control panels for these things are just crazy, with all the different things. I mean, every single area of every pipe and all that has temperature controls and pH adjustments and things like that. So it takes a lot of people to run one of these. So as I said, some of the concerns about nuclear power are the waste disposal, okay, because you can only store it right now, okay. The core meltdown like they had in Chernobyl, but this, we've had some issues in the United States before, when we were first learning how to do this, but now they're very state of the art. I will say this though, that there are some private companies that are wanting to take over the nuclear energy area, and I'm not sure how I feel about that, although, maybe private would do a better job than the government. Who knows? I don't know what your opinion is on that. Also, transporting waste. Interesting, I used to run a hazardous waste treatment and facility, and we transported waste as well. And you will not, like how they'll have those placards on there, and they'll have like little things, and it tells you kind of what the hazard is. You don't see that when they're transporting nuclear waste. You won't even know what that truck has that on there as it's going to Oak Ridge or wherever, because they don't want terrorists to know that it's nuclear waste, so they don't placard it so that you don't know. Now they'll have paperwork inside if something happens, so that if they have a wreck or something, they can figure it out, but it's not going to be placarded, and they don't tell people when they're moving it and things like that, because of the threat of terrorism. Also, how do you shut them down? How do you clean them up after they're no longer viable? That's another issue. So there are issues with the nuclear power, just like there are with others. And so, it just depends. What do you think? What do you think that, is it worth it to not have the breathing issues and all that? I don't know. I'm not going to tell you what I think. After you do the packet, that's one of the things you're going to figure out for yourself, is what you think. All right. It's very interesting, though, so I hope you have fun with it. All right. So mass defect and binding energy. When you form a nucleus, okay, some of the mass of the nucleons is converted into energy, okay, so you're kind of losing something when you do that. The difference in the mass between the separate nucleons, okay, and when I say nucleons, I'm talking about the protons and neutrons and all that, okay, that are in the nucleus. The difference in mass between the separate nucleons and the nucleus as it was is called the mass defect or mass deficiency, okay? Because there's a difference, and it looks like we're losing mass. And so that difference is because of the amount of energy that we're producing, and so the mass is literally transformed into energy. So the energy that is released is called its binding energy. Okay, and so 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules. 1 AMU of mass defect is equal to 931.5 mega electron volts. The greater this energy is per nucleon, the more stable the nucleus is. Because if you think about it, that's how strongly those particles are bound to that nucleus. So, like I said, when I'm talking about nucleons, I'm talking about the protons and the neutrons that are found in that nucleus. Okay, and so there is a difference. This should say AMU. I don't know why it says AU. There's a difference between the helium nucleus and then the parts after I take it apart. The parts after I take it apart appear to be larger. If you notice the number, I mean, it's small, it's a small number, but it does exist. So when you calculate the mass defect, the change in mass, you guess what? Mass of reactants minus products. Okay, so basically you've got, this is the mass of what's in the nucleus when you start minus the parts after you do whatever you do to it. And the difference between those is expressed in kilograms, and it's a tiny, tiny number. Okay? All right. So, and what you do is you use the mass numbers as we know them, and they're on that black and white chart I gave you. It tells you what the mass of a proton and what the mass of a neutron is. And so you use that in order to work these, okay? Because remember that energy is equal to mass times the speed of light squared. So this is not an unknown phenomenon to us, okay? We know that energy does relate to mass in Einstein's equation. So the energy is equal to 3.07 times 10 to the minus 28 kilograms, or 2.9979 times 10 to the 8th meters per second, right? So let's look at this and see how we work them. Okay, so calculate the mass defect and the nuclear binding energy per nucleon, okay, that's important, in mega electron volts for carbon-16, a radioactive isotope of carbon with a mass of 16.014701. So this 16.014701 is the actual product. Okay, so the mass defect, so I got to know the mass defect before I can do the nuclear binding energy. The mass defect, we said, is equal to the parts minus what I know the mass of carbon-16 is, okay? So it's going to be 6 times the mass of the protons plus 10 times mass of the neutrons minus the mass of carbon-16. Now see, okay, so why did I erase that? Okay, so this is going to be the known mass of protons, and this is the known mass of neutrons. How come I have 6 protons? Well, carbon is number 6. I know it has 6 protons. And then the number, the mass minus the number, gives me the number of neutrons, if you recall way back in Chem 1. And so I know I have 10 neutrons. So that's where those numbers came from. So the mass defect is equal to 6 times 1.00783 AMU. That's the mass of a proton, plus 10 times 1.00866 AMU, which is the mass of a neutron, minus, it told me that it was 16.014701 AMU. So you got to use all of those decimal points when you're doing this, okay? So when I plug that into my calculator, I'm going to find that my mass defect is 0.118879. And you can just leave that for now, okay? So that's your mass defect. The nuclear binding energy binding energy is the mass defect. So we call that delta M. Okay, so that's the mass defect in AMUs times 931.5 mega electron volts per AMU. Remember, I gave that to you on that other screen, so that's a conversion factor for you. Okay, so I put in my mass defect, which is 0.118879. That should be AMUs. Times 931.5 mega electron volts per AMU. And that's going to give me 110.74 mega electron volts. And now that's for the whole thing. Okay, that's for the whole thing. If I want it per nucleon, which is what it asks me for, I have to divide by how many nucleons I have. Okay, so I have 110.74 mega electron volts divided by 16 total nucleons. Right, I have 6, that's 6 plus 10, all right, and I get 6.921 mega electron volts per nucleon. Okay, so you have to get the mass defect. So you have to be able to figure out how many neutrons and protons you have. You put that in, you subtract. Now, can you have a negative number? No, you can't have a negative mass defect. It is just the defect, okay? It's the difference. So don't be getting a negative number, okay? And then you put that in times this conversion factor, because we know how many mega electron volts there are per AMU. That'll give you the 110.74 mega electron volts. And then you take that number, divide it by the nucleons if it asks for per nucleon, okay? This is your practice one. I'm going to go ahead and tell you I got 7.66 MeV per nucleon. The back of the book said 7.569, I think. So I think it's a rounding thing. So, you know, just don't worry if you get somewhere close to 7.6, then you've done it correctly. Okay. So all of that stuff we've been talking about is fission. So just a quick thing on fusion. Fusion is where you take two light nuclei, like tritium, which is hydrogen 3, or deuterium, call it heavy hydrogen, which is deuterium or hydrogen 2. And you combine, if you hit those together with enough force, you're going to eject a neutron and a helium nucleus. Okay, so basically you added those two things together and made a helium nucleus. All right, so fusion is what happens in the sun. Okay, because you got lots and lots and lots of hydrogen in the sun, and it's converting hydrogen to helium, and so it's a self-sustaining thing. That's why the sun keeps giving us energy. It has to take a really high amount of energy to start, but once it starts, it's game on. Okay, it produces 10 times energy per gram of fission. There are no radioactive byproducts at all because you just produce a neutron and helium. Unfortunately, the only way that we've made it work on Earth is with the hydrogen bomb. So there are people working on this that are trying to figure out how to control it. Okay, so first, how do you get it started is the big thing, and then how do you control it? Because it's like controlling the sun. So yeah. So anyway, but there are people working on that right now. So you may see things in the news about, you know, fusion reactor, But you know, take it with a grain of salt because it's a long time coming. And that's the end of part 4, and that's the end of our nuclear discussion.